Hello everyone, today we will be going over the Bind 75 in C++, and today we're working with the design, add, and search words data structure. Now before we get started, we are not going to be doing the typical question of the input. Ask yourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and what our output would be. We are actually going to be implementing something very similar to what we did earlier called, with a previous video, implement tree, or try, which was a prefix tree. I'll have the video in the link over there at the moment. And we're going to be using a similar technique that we have already done before. So what I'll be doing is just that I'm just going to go over the steps over what we will need to do ultimately. So starting it off. Step 1, in order to solve the following problem, we need to create a try node structure. We will put inside the word dictionary Step 2, we will have our word dictionary object be linked to a new root we create tied with the try node structure, so we can scan characters. Step 3, we initialize root with a new try node. Step 4, and we'll scan through each character in the word we get. And then for step 5, we will search for the given word in the try. Finally, for step 6, we will return a Boolean value indicating whether the word exists in the try. For step 5, we will have we'll have another parameter for a search function we'll create, and that's going to go into step 6. And if a word is not added, we will put it in the try. Okay, now, just to be able to go about creating this, let me just go this. Step 1. Step 2. Step 3. Step 4. Step 5. Step 6. It'll be a separate structure. So, going down about how step 1 is going to look is that we are going to have a structure called try node. We'll have a try node for children, 26 characters. Then we will have a Boolean to determine is the word. In fact, yeah. And then we will have to define the constructor for the try node. Try node, then is word false. and we are going to set all the characters that we haven't visited to null, indicating that we have not visited anything yet. And we're setting this as children, calling it A. There's here. For every so I'm just going to put the steps further over what we need so we can break it up step by step. So 1, we need to declare an array to hold children nodes. Then we declare a Boolean variable to signify the end of a word. Third part, we define the constructor for try node, and we initialize all the children nodes to null, and then initialize is word to false. So just breaking down exactly for each one, and I'm also going to have the comments down below too. So 1, 2. So we define the constructor. 3. And 5. And then 4. Just how we build it out accordingly. All right, moving over to step 2. The way we're going to build this out is with the following. We're going to declare a new root with the try node. And then for step 3, each part, we set the root to be a new try node. So I'm just going to put them all together right over here. Try node root, and then root is going to be new try node. Then for step 4, what we will have for the next, it's just one step that we have for each, just separating them all together. Step 4 is going to have 2 separate functions, and we have try. Okay. So for step 4, the way we're going to build out this one is that we will start at the root node, then we will iterate over each character in the word. If the corresponding child node for this character is not yet created, and then we're going to move to the child node corresponding to the current character and mark the end of the word. So the way it's going to look for step 4, let me just clarify this. So 4.1, 4.2, 4.3, 4.4, 5, 4.5. So this is how 4 is going to look. Try node equals root, and then we're going to scan through our following word. So car, C, word, And we're going to have 3 and 4 on the inside. Since we're scanning, we just need to check for the following conditions. If we don't have the node, which is referring to the children of the tree, inside of the try, we're just going to add it to the try structure. Children, character, A, equal new try node. And we're going to have a new node moving forward, since we've already determined that there wasn't a node, and we're going to scan to see in the next step. Actually, this will be 4.5 and 4.4. Now, search is going to be unique for this one, given the fact that within our following structure, even though we're implementing a try search structure, what we are looking for as well is that we're also going to have periods as well, or lowercase English letters. So the search is going to be different because we need to figure out in particular on whether or not if it's going to be a character, or then we're also going to have another node that's not going to be. So that's why in particular we're going to create a separate function inside of search that we'll create for entirely if in step 6, just to determine exactly if a word totally exists or not, since we have these following periods. That's really just the big reason that we're going to be doing something different. So for step 5, we'll search throughout the entire tree, and the way how it's going to be done is just going to be one structure. So we will return the instance when we call upon the Boolean value to search for a word using the characters of our given word and the root of the try data structure. So the way it's going to look for step 5, right over here, highlighting it, is that we will return search word dot character string, then the root. And the way we're going to build this out for 6, it's going to be unique. So, step 1 and how we're going to build that 6 is going to be the following. We will start at the root. Root node, and scan for every word and node in the try data structure. Hence we're using root. Root is for the try node that we created over here. It's going to be calling. Make sure as well you put your semicolons. Then while we were doing that, if the index of the current word doesn't equal the following period that we may see over here, then we will scan the next node. Otherwise, we will create a temporary node, and for every character ranging from 0 to 26, indicating we are searching for English letter characters, we will set a temporary node with our children in the try data structure searching for letters and not the following periods. Then if the character is still another period, we will still iterate through until we found a character, then declare true, otherwise false. Let me just put this down here. So the way step 6 is going to look is that we will have our function bool search with constant character for every part of the word, and then we are going to implement our try node and for every index within the word we are searching for every character, and node, we're going to increment I, since we're moving up throughout each of the words in our dictionary, and if the current index inside of one of our words doesn't equal a period, then we're going to continue to scan through the following: children word at I, referring to every single character. Else, otherwise, we're going to create a temporary one. Try node temp is equal to node 1. For int j is equal to 0, j is less than 26, and then we increment j. And for node temp children based in j, if the character is still another period, so we do this with the recursion call word of I plus 1 node will return true. We're just determining if there is another character. Else, we are just going to set that to false. So and then finally we will return the value of our is word. So this will be the last part, which will be return node and node status is word, checking it is. So setting this all up. One, two, and 6.1, 6.2, 6.3 A B 1 2 and then finally 3. Alright, so just giving a whole scope on the rest of our solution that we have. Let me just move this out of the way and just keep the steps. I'm going to also have this in the comment section as well, just to make sure on this. I'm also going to expand upon this further so we can see the full solution, clean up some of the white space. Let me just double check. Yep, don't forget that. And okay. I forgot children. That's what I did. We got the wrong answer. Okay, I forgot another step. Return the is word to true. Sorry about that, folks. 4.6. There we go. Node is word to true. Let's run this. Okay, there we go. Alright, now, just to be able to give a rundown and breakdown over time and space complexity for the following solution is that the time complexity for both inserting a word and performing a search is O of M, where M is the length of the word being inserted / search, and this is because each operation processes each character in the word once. Meanwhile, the space complexity for a try is O of N, where N is the total number of nodes in the try. And we are inserting a maximum of 26 nodes for a character, but then we also have periods at the same time. So yes, this was add and search word. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. As always, take care. Cheers. Bye-bye.